All right, ladies and gentlemen, so today we're talking about lesson 7.1 and 7.2, which talk about the different properties of exponents. So the two skills that we're going to be working on today are the ideas of using structure of an expression to identify ways to rewrite it, and using the property of exponents to interpret expressions. So our vocab terms, the first one today is the idea of a monomial. A monomial is a number variable or a product of a number and one or more variables with non-negative integer exponents. Basically, a monomial is a more complete definition of the word term that we've been using all year long. Remember, the idea of an integer is a counting number, a whole number, no decimals or fractions attached to it. And the other vocab term for today is the idea of a constant. And a constant is a monomial that is a real number. So like 7, -4, a real number. When we're simplifying monomial expressions, the things that we need to do is we need to make sure that each variable base appears exactly once, there are no powers of powers, and all fractions are in their simplest form. The last thing to put in there, because it applies when we get to the quotient rule, is that our exponents need to be non-negative. We want to have positive integer values for our exponents. So to get started with this, I want you to create a chart in your notebook to talk about each of these rules that we're going to learn about. We have 6 of them. So in your notebook, you should have a chart that has rule, and then the symbols, so the way that we express that rule, and then the words to explain what those symbols mean. The first rule is the product rule. In symbols, we would show a to the power of m times a to the power of n is equal to a to the power of m plus n. And in words, that means when I multiply powers with the same base, I can add the exponents. Remember, when we're talking about exponents, that term on the bottom is the base, and the exponent is the power that it's raised to. So when my base is the same, like in this example here, I have a as my base, I can add my 2 exponents. That's really similar to the idea of the quotient rule, where if I have powers with the same base on a numerator and denominator, I can subtract the exponents. A to the m divided by a to the n is a to the power of m minus n. And when we get to the sample problems, I'll show you how we know this is true. I'll show you the expanded form and then where this rule comes from. The last thing is we have the idea of the power rule. The power, or not last thing, the last piece of this part here is the power rule. To find the power of a power, I'm going to multiply the exponents. And again, in the examples, we'll show this out in expanded form and then simplify it back down. A to the m raised to the power of n is a to the power of m times n. These next few rules get a little more complicated. And this first one is the distributive power rule, and it's kind of a combination of a few rules in the textbook. If I want to find the power of a product or quotient, I need to find the power of each factor. So each factor if it's a product, or of the numerator and the denominator if I'm talking about a quotient. AB raised to the power of m is the same as a to the power of m times b to the power of m. If I have the fraction a divided by b, that's equivalent to a to the power of m over b to the power of m. My negative exponent rule tells me that the reciprocal of a to the negative n is a to the n, or the reciprocal of a to the n is a to the negative n. So basically what this means is if I flip the side of the vinculum, if I change the side of the fraction bar that power is on, it becomes the opposite. So if I have a to the n in the numerator, it becomes a to the negative n if I put it in the denominator. If I have a to the negative n in the numerator, it becomes a to the n if I put it in the denominator. And we'll practice with this today. The last one, and this is one just to memorize here, is the zero exponent rule, that any non-zero number raised to a power of 0 is equal to 1. Before we practice with our rules, we're just going to do a quick review of monomials, which ones are and which ones are not monomials. This first one, and these little examples here you do not need to write in your notebook. This is just a quick review. The number 10 is a constant. Constants are a monomial. F plus 24 is not a monomial because it has that expression of addition between it. Multiplication and division, which is really multiplication, are parts of monomials, but addition and subtraction are not. H squared is a monomial. It's the product of variables, and J, a variable all by itself, is a monomial. So now let's practice with our different rules here. The first one, the idea of the product rule, well, let's write this out in expanded form. I see m to the power of 3 and m to the power of 4 multiplied by each other. Well, m to the power of 3 is really m times m times m. M to the power of 4 tells me m times m times m times m. I put multiplication between the two. If I see this here, I know from previous math classes that this expanded form tells me m times m times m times m times m times m times m, which is the same thing as m to the power of 7. I have m multiplied by itself 7 times. If I use my power or my product rule here, this tells me m to the power of 3 times m to the power of 4 is m to the power of 3 plus 4, which is m to the power of 7. Same answer. I can do it in expanded form, or I can use my rule. Well, this next one makes it a little bit more complicated, but it's still the same basic idea. When I see those parentheses there, I don't have anything to distribute because I have monomials. What I really have is just a whole bunch of things multiplied by each other. So what I'm going to do is I'm just going to shuffle around. I know from my commutative rule of multiplication that I can rewrite my multiplication here. I have 5 u to the 4th v, 7 u to the 4th v to the 3rd. So I'm just going to shuffle my pieces around so I have my like terms next to each other. I have 5 times 7. I have u to the 4th times u to the 4th times v to the 3rd. All I've done is shuffled my pieces around because I can do that with multiplication. Well, now if I'm trying to simplify this, I can simplify by putting together what I can put together, those like terms. 5 times 7 gives me 35. U to the 4th times u to the 4th, while using either expanding it or using my product rule, that tells me I have u to the 8th. V times v cubed, well, I know that v all by itself is really v to the power of 1, so that tells me v to the power of 4. So I get 35 u to the 8th, v to the 4th. Now let's try it with the quotient rule, and again I'm going to show you it in expanded form first. That m to the 9th tells me m, 2, 3, 4, 5, 6, 7, 8, 9. That's a lot of m's. Multiplication between each one. And m to the 4th in my denominator. I know from previous math classes that if I have the same term in the numerator and in the denominator that they cancel out. M divided by m is 1, so if I have 1 times anything, it stays the same. So m over m cancels, m over m cancels, m over m cancels, m over m cancels, and what I'm left with is just those 5 m's in the numerator. If it's only in the numerator, it's divided by 1, so I know that that can drop off, and I get m to the power of 5. Well, that's the same thing as if I were using my rule. The quotient rule would tell me m to the 9th divided by m to the 4th is m to the power of 9 minus 4, which is m to the power of 5. This works too with the negative exponents, and we'll get there when we get to our negative exponents. For our next example, again, I'm going to separate this out here so that I have my like terms stacked on top of each other. So I have 4u to the power of 4 times v cubed divided by 12 u to the 3rd times v. I put my fraction bar back in the middle there. Now I can see each piece. 4 divided by 12, well, that simplifies to 1/3. U to the 4th divided by u to the 3rd, well, that leaves me with just u in the numerator. V to the 3rd divided by v, well, that leaves me with v to the power of 3 minus 1, which is v squared. Ooh, I don't know, my pen changed colors there. Let's go back. We're using purple. V squared. My final answer would be 1/3 u v squared. And I could write this out as 1/3 u v squared, or I can leave it as the larger fraction bar. Now let's think about the power rule. Well, the power rule tells us to find the power of a power, I multiply the exponents. But what I really see here, excuse me, is I know that that whole monomial raised to the power of 3 can be rewritten in expanded form. I have negative 2f squared g, negative 2f squared g, negative 2f squared g. If I expand out that cubed symbol, I get this here. And then I can use the same thing I did with the product rule. I can shuffle it around so I have my like terms next to each other. I have negative 2, oops, let's do this kind of multiplication. Negative 2 times negative 2 times negative 2. Oh, that's a different green. I have f squared, f squared, f squared. And I have g, g, g. When I go through and simplify then, negative 2 times negative 2 times negative 2 gives me a negative 8. F squared, f squared, f squared gives me f to the power of 6. G times g times g gives me f to the power of 3. My product rule here, though, or my power rule, can also be combined with that next one, the distributive power rule, which is basically the same thing as my power rule here. But that tells me that that power of 3 really applies to each factor. So if I'm thinking about it that way, I have a negative 2 to the power of 3. I have f squared to the power of 3. And I have g to the power of 3. If I go through and simplify each piece, I'm left with the same answer. This middle one here shows me that power rule. F squared to the power of 3 is really f to the 6th. I multiply the exponents when I have a power raised to a power. Same answer, different way of getting there. Let's practice again with the distributive power rule, this time looking at it with a fraction. The distributive power rule I could write out in expanded form and then simplify, or I could use my rule here to distribute that squared symbol to each piece. I get 2 squared times, a cubed squared times b to the 5th squared all over 3 squared. If I simplify each piece, 2 squared gives me 4. A to the 3rd squared is a to the 3 times 2, so a to the power of 6. B to the 5th squared is b to the 5 times 2, which is b to the 10th, all over 3 squared, which is 9. And in this case here, I'm in my simplest form. There's nothing else I can simplify. That fraction of 4/9 is in its simplest form already. Negative exponents. Well, I know that the negative exponent means if I take the reciprocal, the exponent becomes positive. So what that means is if I kick a negative exponent to the opposite side of a fraction bar, it becomes a positive exponent. So that first one, m to the negative 2, in the numerator becomes m to the positive 2 if I put it in the denominator. R to the negative 3 becomes r cubed in the numerator. And then r to the power of 5 stays the same in the numerator. Now I can go through using my other rules to simplify, and I have r cubed times r to the 5th gives me r to the 8th, all over m squared. Let's do it again with this next example. I have 2a squared times b to the negative 7th times c to the 10th, all over 6 times a cubed times b squared times c to the negative 3rd. So the first thing I want to do is I want to flip around those pieces that are negatives to turn them into positives. So I get 2a squared, I kicked the b to the negative 7 downstairs, c to the 10th, well, c to the negative 3 comes upstairs. I have 6a cubed, b squared, and the b to the negative 7th that I kicked downstairs, kicked to the denominator. Now when I simplify, that 2 over 6 can simplify to 1/3. A squared over a to the 3rd is 1a left in my denominator. My b's, well, I have b to the 7th times b to the 2nd, so that gives me b to the 9th. And I have my c's, c to the 10th and c to the 3rd in the numerator gives me c to the 13th. Last one's here, that rule, the zero exponent rule. Before I need to figure out anything on the inside, no matter what that is, if it's raised to the power of 0, the answer is 1. So on the homework, number 14 on the worksheet, this one combines a few of the different rules, so I figured I'd throw this one in as our last practice problem. I have 6f to the negative 2 over g to the third h to the 0 over 54f to the negative 2 g to the negative 5 h cubed. Well, what we're going to do here is, again, we're going to rewrite them out so they have a little bit of space so we can think about each piece. 6 over 54, f to the negative 2, f to the negative 2, let's go purple, g to the third, g to the negative fifth, and h to the 0, h to the third. When I put this all together, then, I can simplify. 6 over 54, well, both of those terms are divisible by 6, so I get 1 over 9. F to the negative 2 over f to the negative 2. Well, I can use a few different rules here. I can use my idea of negative exponents and kick 1 to the numerator and 1 to the denominator. I can use my quotient rule, or I can use my idea that I know that those are going to cancel out. So I have no f's in my final answer. G to the third divided by g to the negative 5. Well, this is where I want to use either my quotient rule or my negative exponent rule, and I find out that I'm left with g to the 8th in the numerator. Last one, h to the 0. Well, h to the 0 is 1, so it goes away effectively, and I'm left with h to the third in the denominator. So my final answer would be 1/9, and then g to the 8th in the numerator and h to the third in the denominator. Lots of different combinations of rules there. Your job tonight is that homework assignment, worksheet 7.1 and 2, which is just one worksheet. I put both sets of exponent rules together. When you are finished, please submit the image of your assignment on Teams. You can print out the worksheet and fill it in on the worksheet, or you can solve it in your notebook and upload a picture of your notebook page. I will post the key later this week, but I want to see what you come up with first. I'm hoping that this section is mostly review and that we're on the right track. Thanks, guys.